Welcome back to Book Club. Again, Aircraft Engine Design. This is a great book. Go get it. Let's go read through together. And especially remember that there are design examples throughout this book that really kind of drive as we sort of go from the systems level down, down, down into the components. And so to kind of keep you motivated on this, I wanted to show a couple engines here. This is the F-16, sort of the original block engines, the F-100. And it's an amazing, engine. And really, the F-16 was almost this new idea of energy climbing. We'll get into it. It's that performance is energy, and energy is altitude, and your or speed, and so your energy climbing is how quickly you can climb. Again, in that sort of speed altitude front. We'll get into it. So the F-16 was really the first one kind of designed about that. And John Boyd, Major. I forget we retired at Colonel Boyd, I think, but he was really the fighter pilot associated with changing how we think about fighter combat from that energy management point of view. And really, the F-16 was sort of that first fighter. And this is successful. And the F-16 is 4,600 copies of the F-16, of course, flown by air forces around the world. And this was the Pratt & Whitney was actually the first engine, and then the GE F-110 is also part of it as well. And so just an amazing, single engine fighter, but you really get a flavor for this book on this sort of advanced aircraft fighter, how, it's effectively an F-16 type replacement is where it gets into. So you'll really like it. And so here's just a couple pictures of the F-16. It's really just basically a flying engine. If you think, my other fun aircraft I'm a fan of is the A-10. It's basically a flying gun. What happens if you build a gun and then wrap an aircraft around it? This is effectively build an engine and then wrap an aircraft around it. It's basically what the F-16 turns into. Okay, and again, I think this article says it best. F-16 is the most dominant fighter of its generation. So, aircraft basics. I remember that this book all starts with the fact that you've had like a Kuchuman class, or you've gone through the Rainbow book. Basically, the idea of, hey, you've already had the basics of aircraft design, and so this is a very simple warm-up, takeoff, climb to your altitude, hold that cruise, loiter, and then land. Now, if you're designing a fighter, and then the book will go into it, there's you might have climb, you might have like supersonic penetration, you might have come down and strike a target, climb back up. Accelerate to get a, not supersonic cruise, but like skedaddle, like a high supersonic flight out. And then, there's all the requirements that can show up from a military point of view. In fact, I've even seen civilian versions where this is way too simple, where it's actually a loiter landing attempt, come back up to a sort of lower cruise altitude to get to the next airport and then land. So really the whole idea here is that aircraft, while we can think about thrust to weight and kind of take off and wing loading and things like that requirements, a lot of it will stem from the mission. And honestly, depending what the mission is, it puts very different requirements, not only just on the aircraft design, but also on the engine, which is where we're sort of getting into. Okay. All right. I'm going to leave this. Actually, I'll go back to. All right. I'll leave this here for now. Okay. So we're in chapters 2 and 3, and I already kind of pre-drew my awesome aircraft here, so I don't have a ton of things I have to keep pushing at. And so really, you have to get into this with a whole bunch of extra angles. Okay, it's not just as simple as we normally like to do it. Okay, so the wings, yes, there's lift. That's normal. We want to account for the fact that thrust may come off at a different angle. I believe that angle we'll use in the book is phi, so we'll stick to that. This is the center line of the aircraft, and so that's just saying that the thrust can be installed slightly off center line. At an angle slightly off center line. The actual flight of the aircraft is this, right? It's not you're not flying at the center line. You're always going to have some sort of flight. And so this is the sort of loading of the wings, if you will, and I'm not accounting for any wing angle, which you can get into. This is what we would call angle of attack, and then this is theta, which is the flight angle of the vehicle compared to the horizon. Right? And so with that, then that's gravity. And this angle is also theta. And then, of course, you have drag, which is going to go along the lines of flight, right? Along the lines of that, if I draw that out. Again, this is sort of the AOA, right? Get the flight angle. This is drag. And then it's usually written as the drag plus residual drag. That's simply because an aircraft will have a clean configuration, which is drag, landing gear tucked away and all this stuff, and then R would be landing gear deployed and things like that. Okay, and so when you walk through, basically parallel to velocity, you get all of this sort of aligned. So thrust, cosine, alpha plus phi. And sorry, I'm going to shorthand this to alpha. I know the book doesn't. I'm going to get tired of writing AOA. So I'll introduce another alpha. So this is alpha plus phi, and then minus the weight of the aircraft sine theta. Again, right, the weight of the aircraft. The weight of the aircraft would be this, and then you pick up the sine. And then minus, again, the full drag plus the residual drag. That's equal to the weight, g, and then a parallel. Weight just, again, weight is a force divided by g is now mass. So this is mass times acceleration. And which is weight over g, dv dt. Okay. And then if you do it perpendicular to v, I really should have done it in a different color. Then you have lift. This is the lift force there, plus any contributions from the engine, T sine alpha plus phi minus W cos theta is equal to weight over g, and then parallel acceleration. All right. Then the next step here, where we're headed, is that energy diagram I was talking about, and I flashed for a second. And so then if you dot, this is take parallel and dot it with V. And so then you have thrust, bracket, thrust cosine alpha plus phi minus drag plus residuals times V is equal to weight, and this is V sine theta plus d by dt of v squared over 2g. And that's just basically compacting that into a v squared. Okay. Now, we're going to assume that phi is small, which it usually is. Okay, angles of attack are usually pretty tiny. And so then you end up having thrust minus drag plus residual over weight times v is equal to time rate of change of altitude plus v squared over 2g. So there's your energy. Okay, and so that's basically the time rate of change of effectively z, or z. I can put on my original Canadian accent for you, which is basically the power. Okay, so this is where Boyd came from. Okay, in that whole analysis, and so that's what gives you this, right? So here's a picture from Antonakis et al. It gives you this sort of these are constant energy profiles. Okay, and so what this paper was about was solving the path. So there's a min time to climb, and there's a min fuel. So if you're trying to get up to, say, this final point here, which is Mach 1.7, and of course this is in meters. 15,000 meters is close to, that's almost 45,000 feet. So it's probably at 13,000 meters to 39,000 feet. That sounds right. Okay, so 40,000 feet, Mach 1.7. Right? What is the fastest way to get there, starting from zero? And so you see that. In fact, this is going to show, from that minimum energy point of view, What's the basically it's the fastest hill climb, and you go do that. You can see here you would punch it to the point of a Mach 0.8. So now you're going fast, and the engine is roaring because you're at sea level, and then you would I think it's called a zoom climb, and then you pop up. Now you would basically climb without doing too much speed, and then you would pop over. Okay? And this is basically what you're doing here. These sorry, I think these curves are, yeah, it's the power curve. Yep, there it is, right there. So it's this PS, and so then away you go. So this is tied into the engine performance, min fuel, min time to flight. So this is really really pretty advanced. Okay, and so that's the biggest. Again, like credit for this idea really goes back to Boyd, and whether like all things, he was the one that got the sort of the Air Force and system to think along these lines. I guarantee he wasn't the one who invented it. It's usually some scientist who wrote some paper back in the days, but credit is given to the people who actually turn it into reality. Okay, that's usually the way it happens. Although I'm sure if you listen to him talk, he would tell you where the idea came from. All right. So now for a couple other unfortunate symbols. So we defined theta and delta before, and so this one's going to get real annoying, and I'm going to have to pay attention to my notes and things like that. And so thrust lapse is alpha times the thrust at sea level. That's going to get damn annoying because I just wrote alpha here, right? And then alpha is going to turn into something else once we get into engines. So this is weight, then is beta times your weight at takeoff, which also gets annoying. Beta is used for a whole bunch of different things. And then N is a load factor. And so if you're turning at 5 Gs, that N would be 5. Okay, that's basically where it comes from. And so all of the thrust relation, this is kind of pulling back to, again, a Raymer book or a Kucherman book. And so thrust at sea level over weight at takeoff, that's the plot that we were looking at. Thrust to weight is then beta over alpha, drag plus residual over beta weight takeoff plus power over V. Okay, which is then equal to, and there's a whole bunch of dots here, right? My goal is not to derive all of it for you. It's all in the book. So go through and make sure you understand some of this derivation. And I'm going to try and see if I can get this well. K1 n squared beta over dynamic pressure, wing loading, plus K2 times your turn, plus CD0 and CDR over beta over Q, and then there's wing loading again, plus beta over V. Okay, that's the one, when we show those curves of sort of, thrust to weight versus wing loading, and you have sort of all of these requirements and things like that. This is where a lot of it's coming from. These are all just different configurations of this. Choose this and you get this thing. Choose this and you get this different thing. Okay. K1. So to give you an idea, K1 is effectively your drag effect, and it's not dimensionalized, right? But we do see it sort of kick off and get larger with Mach number. Same thing with CD0. You sort of have a step change when you're crossing Mach 1. Okay? And, as we sort of get into the engine side, where you're then going to see become really kind of challenging is that this is theta. Okay? So theta 0 over theta standard. And then really you're going to want to have, this is combustor temps. What's going to become the limitation, and this is a thing called theta break. So your compressor, whatever it is you're doing to compress the air inside the engine, it makes it hotter. So compression always makes it hotter. And so as you're flying with Mach number, and you're increasing your Mach number, right? You're increasing your theta. And so that's the temperature of the air. The air coming in, no matter what your inlet is, and we'll get into inlets and things like that, but that air is being compressed when you're supersonic. Okay, it's coming in, it's getting compressed, and then the jet engine is compressing it more. And so what you end up having is that if you don't do something, your jet engine is going to melt. Now, once you get up to about Mach 2.5, it's going to sort of melt anyways. That's one of the challenges of hypersonics. And so that's why here at Venus, we're actually doing a rocket-based combined cycle. We feel like it solves all of those challenges versus a turbine-based combined cycle. So it solves it with a little bit more mass from the aircraft point of view. But you have this theta break anyways in regular aircraft. And so you're going to have a profile where your engine's going to run up to a certain temperature, and then it's going to have to adjust off of this. So that's one of the biggest things with the engine. And then we're going to see kind of throughout this as well, a little final diagram. You're going to end up seeing also, this is now range, okay? Unfortunately with ours, you're going to see that there really then is sort of a sweet spot from a performance point of view, where your maximum range, right? You're going to have sort of this would be your let's say this is Mach number. This is your cruise. There's going to be a singular value at the aircraft level where you're going to have the best range. Okay, all of these end up rolling up to the aircraft, and so it really is kind of this back and forth between engine designers and aircraft. So I'll end with a fun story. Okay, that aircraft engine integration is not easy. All right, you're going to see throughout this book all of these trades back and forth to the aircraft level. In fact, we were talking to a couple privileged to Venus. We've been able to have some conversations with some amazing executives of companies I can't name. Okay, all the big aircraft companies. One of them overheard us talking about like engine development and cost, and so integration. That to switch from one engine to another, say to go from GE to Rolls-Royce engine on a large aircraft, is about $1 billion. Okay? There's no such thing as just bolting an engine. You have to go do all of these studies, airframe integration, structures, vibrations, certification, all of this stuff. It's not easy to just have a new engine. I started off this video showing the Pratt & Whitney engine and then the GE engine for the F-16. Like, none of that was cheap. Now, it was worth it for the government to go have multiple engine providers and compete it out, absolutely. But none of that's cheap, right? And then, what was the second story I was going to tell you? I blanked out. There's another story. I'll remember for the next video. I'll start off with the next video. It was what another air executive was saying about engine design. Okay, yeah, it's not coming to me. All right, so we'll see you next time. This is sort of the basics. Chapters 2 and 3 is the basics of flight, and really, there's a whole list. So this equation, all of these lines show up. Go take a look at all of the different lines. It's like cruise and climb and constant altitude turn and all this different stuff. So go familiarize yourself with this again, because this is basically our Bible and starting point as we go from here. But I remember the story. Okay, the story was Boeing. Initial Boeing was actually an engine company, an aircraft company, and an airline. Right? It was Bill Boeing had it was doing airmail and all this stuff, and then started taking passengers, realizing passenger flight was paying way better than airmail flight. Now the story goes, in the 1930s, Boeing, like this whole now burgeoning aircraft industry, was actually doing well, as most of the other industries were not. It was a depression, and there was a U.S. senator, I don't remember, that basically took the lead to declare Boeing a monopoly and shut it down. And so the airline that Boeing had started became Continental, which was ultimately United. And then the engine company became ultimately what we know as Pratt & Whitney, and then Boeing, aircraft company, stayed Boeing. And so they took Bill Boeing's company and they split into three. And I believe Bill Boeing never came back. He sort of said, forget it. So I say that to say, aircraft engine and aircraft engine used to be one and the same. And that the integration is very, very, very complicated. And so I know it's separate now. You have all these different aircraft companies, and you have engine companies, and that's a separate thing. But there's something to be said for vertical integration on something that is this complicated. In fact, in the rocket world, there's only one company I know of that is trying to do separate rocket engines and then selling to launch vehicles. Just that integration is actually worse on the rocket engine side, which is why every other rocket company is usually I'm talking about commercial, like SpaceX and Virgin and Relativity. All these rocket engine companies are all doing it themselves. So, yeah, this integration is key. So make sure you understand. All right, we'll see you next time.